Thanks for having me. We heard a lot about hardware, so now you're going to hear about software. Hopefully that's going to keep you awake until the end of the day, as I'm the last speaker here. And more specifically, the role of digital twins in accelerating our path towards quantum error correction and ultimately to fault-tolerant quantum computers. So I'm going to oversimplify here a bit, but when we look at the stack of that is needed in order for us to ultimately get to quantum applications, we would like to have better hardware through a software control. We would like to reduce the noise on the circuit level. We would like to reduce the errors as we're doing quantum error correction. We would like to have higher fidelity algorithms that ultimately would lead to a larger range of applications. And to say the obvious, unlike classical devices where you need to flip a transistor and you apply a bias to a gate and you switch from 0 and 1, which the physics is kind of very well known, in quantum devices, as we saw, software has to be hardware aware. Why is that? Because different modalities have different ways of controlling and manipulating those qubits. As you compose and make your qubits work, you then take them to the circuit level. Those circuits have kind of different noise models as you propagate through time and make those qubits then aggregate into logical qubits that take you to error correction, etc. In other words, if you're able to be what we call hardware aware, your path towards controlling every layer in the stack in a more accurate way is accelerated. And that's kind of our mission statement at Quantum Elements. We're a Southern California quantum startup, so it's great to be here. So what are digital twins? Digital twins is the ability to describe the device physics from first principle at a large scale, meaning you need kind of two superpowers. The first one is to be able to look at the system in front of you and describe it from first principles. We're using master equations in order to do that, meaning we are looking at the system Hamiltonian, very low level, understand how the system works, and we know how to do it at the scale. So I'm going to take you through this talk and how do you not only achieve that and use that, but also how do you scale it to a scale that is interesting enough to tackle most of the problems that you're dealing with in quantum devices. So now that you have those digital twins, what our customers are able to achieve, they're able to design virtually better hardware. Why? Because before they go and cut metal, like we saw, and understood how expensive and time-consuming it is, they can virtually play with different pulses and different configuration to achieve better fidelity gates on their 1 and 2 qubit gates. Once they've done that, now they can take those optimized systems, those optimized qubits, to the circuit level and run circuits and understand how to deal with errors and noise that accumulate on the circuit level. So implement some of the techniques that we have in-house that relates to error suppression and error mitigation. Now you've moved from the circuit level to more complex components like error correction, where you look here at surface code. You're able to look at large enough system to develop hardware-aware decoders, meaning to have a deep understanding of the noise models of your system when you're looking to develop those decoders, and ultimately that leads you to applications. So let's take a specific workflow, and then I'm going to show a couple of examples with the work we're doing with Rigetti. And the workflow is very simple. You start with calibrating the gates. You're providing error budget, meaning what is the composition of errors that make your gate perform the way they're performing. Then you're minimizing the noise through multiple optimization cycles. Ultimately, you take those optimized systems, and now you can go to quantum error correction through a process that is known as co-design. So the first step is to provide a canvas that gives you very large flexibility on how you're building your virtual quantum processor, your virtual QPU. You can do it for superconducting qubits. We now demonstrated this capability for neutral atoms. And effectively, you can go and build a virtual representation of whichever system you're interested in, connect them in whichever way you would like to, and insert the noise models that represent your specific system in your specific setting. So that's almost like a superpower where you want to control each parameter of this virtual machine. Obviously, you can think on different noise models that you can insert there, et cetera. And once you're happy, you just upload your file and run a circuit. Now that you've kind of constructed your QPU, I told you that you can also optimize how they perform. So you can virtually dictate which kind of qubits you're interested in, gates you're interested in developing, and go to a virtual environment where those gates can now be manipulated virtually and get to a point where you can run whatever kind of optimization cycles that you want in the presence of other qubits. And that's very important because one of the things that we know that most systems have is this effect, crosstalk effect between the different systems. You can do it for a single qubit gate. This is for a 2-qubit gate in the presence of other qubits. So now that you know what kind of qubits you would like to realize, we are optimizing them to a point where they're working in the best theoretical fidelity and taking them to your system, your physical system, and allowing you to see the full noise composition of your system. This is a work we've done with Rigetti, where you can see how the different noise parameters, the T1, the T2 leakage. Leakage is, you're working in a 2-level system, but sometimes you have leakage to a higher excited state. It's a phenomenon that you would like to avoid. So if you know the portion of your system that is exposed to leakage, it's something that you can then go ahead and deal with on the hardware level. So on top of breaking down very nicely the different contribution of different noise models, you can see that our tool is also allowing to save a lot of time because we are optimizing virtually before you go and implement on the hardware. Not only that we've done that, we were able actually to identify a new noise source that was affecting the performance of the hardware, and that allows the experimentalist to then go and put a lens on this specific noise model and address it in the design process. So what is really the difference between running a simulation of a system versus a digital twin? So when you look at a simulation, and you have many simulators out there, you're actually looking at the kind of algorithmic level. A digital twin is looking at the device level. So you can see the difference in the representation. On the left-hand side, you see a quantum circuit. It's abstracted. There is no time evolution of your noise system. But on the right, you can see that you're starting really with the physical description of your system, then you're deriving the full representation of how the system behaves, and then the noise model. And it allows you to really look at the device physics and how they evolve over time to then go address the kind of core problems in making those systems scale. Now, the thing is that it comes with a cost. And it comes with a cost because you need to solve how a quantum system evolves over time in the presence of noise and how those two interact. And it's very expensive computationally. If you look at brute force solver, we're talking about 16 qubits. Obviously, if you can scale it indefinitely, you don't need a quantum computer. There are other methods out there. Tensor network have a bond issue. They cannot deal with very deep or highly entangled systems. So what we've done is we've used a version of Quantum Monte Carlo to look at systems that are sparse and noisy at a very large scale. So we're taking kind of the whole universe of solutions through stochastic sampling. We're looking at different areas of interest. And based on that, we're building a new capability that allows us to scale way beyond what was thought to be possible in those kind of systems. Can say that this work was just accepted to PRL. It's going to be out in next week or so. So you can see here that if I've shown you that with brute force you can get to about 16 qubits, we are showing that we can go all the way to 97 qubits and actually do it very economically. So on relatively modest computer resources, in about an hour, you can get 97 noisy qubits running on a surface code, which is one of the techniques used to get to logical qubits, taking an ensemble of physical qubits and using them now to solve problems at scale, because the noise levels are low enough that as you grow the number of qubits, the noise actually goes down. But one of the things that we're addressing with this large-scale capability of noisy qubits is how do you develop decoders that you can actually trust? So Alan Ho said something very interesting that resonates with me: garbage in, garbage out. If you don't know what you're inserting into the system, the answer that you're going to get is probably not the right one. So the go-to platform today is Google Steam on the right, and there is a good reason Google Steam has no colors. It's because it's not aware of all the different hardware-level noise models that are taking part in making the system work. On the left, you can see the work that we just published with AWS a couple weeks ago, where the colors and the change in the color represent syndromes that are related to noisy systems at a very large scale, scales that were not deemed possible. So if we take it now to the next stage, we can think about how will the future of decoder development would look like. If we know that Steam on the bottom is highly optimistic, if we know that reality is probably much worse, can we use large data sets in order to close the gap between what we think the reality is to what reality is? And I would like to leave you with this image here that gives you a hint to the capabilities of digital twins to close this gap. So what you see here on the right, we took distance 3. Actually, most systems out there today are able to implement distance 3. Distance 5 is somewhat too big. So we took distance 3, surface code on the right. These are 17 noisy qubits. And we ran 120,000 runs of those simulations, of those digital twins. Each run took us about 3 seconds. Now, because we're running them on very modest computational resources, we can parallelize the approach. We can do 20, 50, 100 in parallel over 3 seconds. Within a few hours, we got to 120,000 runs. But what we've done is very unique. We were able to change hardware parameters while we were running those digital twins. We were able to change the T1, T2, the crosstalk, how those qubits affect each other, gate miscalibrations. You cannot do that on hardware, right? Because the T1 is kind of given. You can maybe calibrate and get a bit more out of the system. Crosstalk is kind of a hardware thing, but you can do it virtually. We also started the surface code in different logical conditions. You can see them. And each dot here represents a state of fidelity. So using this kind of varying landscape where time evolves of this system, you can see the places where the fidelity is at its highest point, which is the Z, and its lowest point. Now, I would just leave you with the thought that one run of our digital twin gives you the full picture of what's going on in your system, because we're solving all the master equation from the grounds up. In order to get the same level of fidelity from a quantum device, you need about 100,000 shots. 100,000 shots takes, a few minutes. Now, think about the fact that you have 1, maybe 2 quantum computers at your disposal. If you're, and now a few minutes, 1 computer, a few thousands of dollars per hour. Think about the cost of getting to 120,000 data points on a quantum device that will allow you to build the same richness of data to take you to hardware-faithful quantum error correction. Thank you. Thank you very much.
So one of the questions that, one of the things that are very hot right now are these QLDPC codes. And depending on what kind of code you're using, there's different trade-offs that one may need to make. For example, making very long-range connections versus making more local connections. How would this software be used in order to inform what kind of QLDPC codes, how big the code, I mean, what are the different hardware trade-offs that one can use?
It's a great question. We actually have 2 customers already that are working on QLDPC. And one of the things that you can do virtually using a digital twin, because we're starting from the system Hamiltonian, is really describe those long-range couplers. Obviously, you'll have to rely on some understanding of your of the system, but then the benefit of working on this parallel track is that while the hardware teams are working extremely hard on realizing QLDPC that requires some very fancy and advanced lithography capabilities, the quantum error correction teams can start developing the decoders and the approach to do that. So it's definitely something that that the system is being used for, including, by the way, readout, which is another big deal.
Could you please talk to us a little bit more about the new kind of noise you found and why it's different than the others?
It's part of their system in terms of customer confidentiality, so it's hard for me to talk about.